Welcome everyone. Thanks for joining us. I'm Ian Stewart. I'm going to be your host, really, to take us through the next 1.5 hours. And as I'm sure you know, the topic that we've got today is our hazardous Earth, which is essentially a trip through. Well, it says the most extreme natural hazards, but as you'll find out really in this session, one of the points that's probably come through is there really is no such thing as a natural hazard, in the sense that most of the hazards are unnatural and all coupled with the messiness of human activity. But we'll be looking at tectonic hazards, we'll be looking at climatic hazards, earthquakes, volcanoes, storms, climate change, and really the work of geographers in the broadest sense, really, to study that. So I say I'm Ian Stewart, and I'm at the University of Plymouth. I'm Professor of Geoscience Communication there. In terms of background, my background is an earthquake geologist, but I've worked on tsunamis and volcanoes in different ways, but most of my attention really has been on communication, communicating particularly hazards and climate change to non-technical audiences, normal people, if you like. So I've really got a fantastic set of panelists today that's going to cover quite a variety of different topics, and I'm delighted to introduce the first of these. It's going to be Dr. Rebecca Williams. Becky is a senior lecturer in geology at the University of Hull. She's a volcanologist, and it says on here an igneous geologist, which I guess means you started as a melt then, Becky, but your research really looks at kind of very active volcanic processes, hazardous volcanic flows in particular, very interdisciplinary, lots and lots of different techniques getting brought together with modeling and chemical analysis and fieldwork to understand volcanoes. Our next panelist is going to be Dr. Solmaz Mohajir. And Solmaz is at the University of Central Asia in Tajikistan. Well, I don't think you're there today, but that's where you're actually based. Very broad interest in kind of geological hazards, mountain hazards, earthquakes and rockfalls in particular, and again bringing together a wide variety of techniques around more the monitoring, remote sensing, geographic information systems, surveying, things like LiDAR, and as is Becky, really interested in the communication problem, really, particularly between scientists and the public. Thirdly, we've got Professor Bruce Malamud. Bruce is Professor of Natural Environmental Hazards at King's College in London, interested in a wide gamut of hazards, wildfires, earthquakes, landslides, floods, tornadoes, and particularly how they interact actually and how they trigger each other. And he's also very experienced across the hazard field, and so is executive editor of a journal called Natural Hazards and Earth System Sciences. And then last but not least, we've got Professor Pete Stott. Pete is a science fellow in climate attribution at the Met Office. We'll hear a lot more about what climate attribution means. And he's also attached to the University of Exeter. He's an expert in the attribution of climate change to anthropogenic and/or natural causes, and really looks at extreme weather events and human-induced emissions of greenhouse gases. So that will be bringing in the climate change dimension. So welcome everyone, welcome all the panelists, and really what I'd like to do, just to explain to those of you listening, I don't know how many we've got, but we're expecting about 250 or so coming in. And what we'll do is I've just asked everyone to introduce themselves with a short outline of what they're interested in, what they do, maybe with a couple of slides to illustrate that, to get us going, to set the scene, and maybe the kind of key questions that's emerging from their area. And then what we'll do is we'll have a general discussion around some of these topics. And I've got an eye on the chat. And so what we'll do is we'll have a look at some of the questions that's coming in. So if you are interested, put into the Q&A your questions and we'll try and pick those up. And then we'll zip our way through. I have to say that, as I say, although this is set up as so-called natural hazards, we are going to be traipsing right across the geographical area. I sometimes say that I got into, I took geography and geology at university because I liked physical geography, but I didn't like human geography. And usually when I do this in an open forum, half the audience smiles and half the audience sighs. But I have to say also in the last few years, I've realized what a terrible mistake I've made. And most of my work now is with human geographers. So I've tried to make up for it. So we are going to be covering the broad territory. And the perfect way to get us started on this is from Becky, because Becky covers a lot of that ground in relation to volcanoes. So Becky, take it away, please.
Thanks very much, Ian. I will just share my screen with you all. Hi, so thanks for that introduction. I won't repeat my name, but I'm a volcanologist and I'm currently working at the University of Hull, where I teach earth sciences and geography. I study volcanoes on land, at sea, whether they're currently erupting or long extinct, even including those in the UK. I'm primarily a physical volcanologist, and I'll explain a little bit about what that means later. But increasingly, as Ian said, I've become interested in the interactions between volcanoes and society, how they interact with each other, the impacts, their co-evolution, and how we communicate to the communities that are at risk from volcanic eruptions. A volcano can erupt in many different ways, from gentle, effusive eruptions to violent, explosive eruptions, the impact of which can be felt tens of kilometers away. The hazard that a volcano poses depends on the eruption style and size, as well as the proximity of communities to the volcano. The biggest hazard posed by volcanic eruptions are pyroclastic density currents. You might know these as pyroclastic flows. Since 1600 AD, these have killed over 90,000 people. Pyroclastic density currents are flows of gas, ash, and rocks that travel down the slopes of volcanoes. They can be several hundred degrees Celsius, and they can travel up to 450 miles an hour. They're incredibly destructive. They destroy anything in their path, and despite what Piers Brosnan might have you believe in Dante's Peak, you will have little chance of being able to outdrive them in a jeep. They were the cause of the destruction of Pompeii in AD 79. The next single biggest hazard that a volcano poses are tsunamis. These have killed over 55,000 people historically. Volcanic tsunamis can be triggered in a number of ways, and may even occur when the volcano is not erupting. They can form when a pyroclastic density current enters the ocean, when a volcanic slope collapses in a landslide entering the ocean, or during violent submarine eruptions. Finally, I just want to introduce you to lahars, and these are the volcanic mudflows, and these have been responsible for over 37,000 deaths. These form when heavy rains mix with volcanic sediments, or when eruptions melt the snowpacks that you find at the top of some of our tallest volcanoes. These can occur during an eruption, but they can also occur many years after an eruption, particularly at volcanoes which experience heavy rain, such as during storm seasons. And so these are a long, protracted type of hazard that many communities face. You'll notice that I skipped over part of this chart here called the indirect causes. And these are causes such as starvation and disease that can happen during eruptions that can change climate and cause extreme weather, or eruptions that force evacuation into refugee camps where disease becomes a problem. When we look at the data on how many people have died over the last 400 years or so, we realise that 5 eruptions are responsible for almost 60% of all deaths. So this graph here, the red line is all fatalities cumulative over that period of time. And then the purple line and the green line are those big events taken out of the data set. And so you can see that the cumulative deaths here are punctuated by these 5 events. In 1792, a landslide at Mount Unzen in Japan caused tsunamis which killed almost 15,000 people. The 1815 Tambora eruption is one of the most explosive eruptions in human history. The ash and gas plume from the eruption column dispersed around the world and changed the climate, triggering extreme weather and harvest failures in what became known as the year without the summer in Europe. The 1883 Krakatau eruption caused pyroclastic density currents which traveled into the Sunda Strait, causing tsunamis that swept the Indonesian coast. The volcano eventually collapsed into a caldera in which the Anak Krakatau volcano has grown, and this volcano itself caused a deadly tsunami just 2 years ago when a portion of the volcano collapsed into the ocean during a relatively gentle eruptive episode. The eruption of Mount Pelée on Martinique in 1902 is often considered to be a marking point for the birth of volcanology as a scientific discipline, as it is one of the first eruptions where professionals identifying as volcanologists attended to make observations. During the eruption, pyroclastic density currents destroyed the city of Saint-Pierre. The most recent of these big 5 eruptions is the 1985 eruption of Nevado do Ruiz in Colombia. A relatively small eruption, this melted the snow cap on the volcano, and the water mixed in with the ash from the eruption and descended the volcano, destroying the town of Olmedo. Mitigating these volcanic hazards is a goal of much of volcanic research. Volcanologists use a variety of techniques to better understand volcanoes and their eruptions, from understanding the processes that occur deep within the Earth's crust that cause eruptions, to studying the ways in which a volcano can erupt, to assessing the impact of eruptions on communities. They do this in a number of ways. Some volcanologists study the deposits from eruptions to try and interpret how the volcano behaved in the past. Some use geochemistry to try and disentangle what's happening in the magma reservoir deep in the Earth's crust. Some use computer modeling, some use remote sensing, and some use historical data, and some try to simulate volcanic processes using models in the lab. Volcano observatories monitor volcanoes, looking for signals on the Earth's surface that a volcano may be building up to an eruption. For me, I take an interdisciplinary approach. The main focus of my research is on hazardous volcanic flows, particularly pyroclastic density currents and lahars. I study the deposits of these in the field. So I go out to a volcano, typically ones that haven't erupted for many years, and I look at the deposits and I do some geological field work, trying to understand how the deposits were formed and what that can tell us about the behaviour of the currents that formed them. A difficulty with this approach is that we rarely observe these processes happening in real time, in real life, in enough detail. Certainly, if you were close enough to make these observations, you'd likely not survive to report your findings. So there's a disconnect between how we interpret our deposits and perhaps the real physical process that were happening in the currents. So we use laboratory models to try and recreate these currents. In our flumes, we can observe details of currents like lahars and pyroclastic density currents. We can observe their behaviour and directly link these to the characteristics and the deposits that we form in the lab. This improves our ability to interpret the same deposit characteristics seen at real-life volcanoes and ultimately improve our hazard assessments. Hopefully, this will reduce the chances of another extreme volcanic tragedy happening in the future. But before I finish, I'd like you to think back to the big 5 eruptions I've previously mentioned. Each volcano erupted in very different ways, from a relatively small ash eruption to the biggest in human history, but each resulted in a similar number of deaths. And this is one of the challenges that volcanology faces. Each volcano is different, and each eruption is different. We tend to understand a small number of volcanoes in great detail, and we can identify typical behaviour. But there are many other volcanoes that are surprisingly barely studied at all. Sometimes a volcano can erupt that we know little to nothing about. Or a volcano that has a typical pattern can suddenly erupt in a way that is atypical. How then Can we be effective in managing a volcanic crisis with such uncertainty?
Oh, you left me hanging there. I thought you were going to answer it, but I guess that's the whole point of the panel. So that's great. That's definitely left us some stuff that we're going to come back to and pick up on. Thanks for that, Becky. So, delight then to introduce Solmaz, who's going to talk to us about earthquakes and about her work, particularly in kind of Central Asia, I think, and sprawling into the education and community engagement side, which is another area that we'll pick up. So please, Solmaz.
Great, thanks, Ian. I'm gonna share my screen with you in a second. All right. Okay, great. Thank you everyone for being here and for being interested in natural hazards here. So let me tell you a little bit about my work and how I actually fell in love with the work that I got doing 15 years ago. So it all began when I actually landed in Kashmir in northern Pakistan in 2006. And this was after the 2005 Kashmir earthquake. This was a devastating earthquake. It took the lives of more than 80,000 people. So I was there to set up a GPS station, such as the one that you see here on the left side. And what does a GPS station do is that it measures the ground deformation or the change in the shape of the crust due to the earthquake. So we can do this by tracking the position of a point on the surface of the earth over some period of time, and that can give us the velocity or the speed of that point and the direction. Now, after that trip, I also began working a little bit more in other places in Central Asia, including Tajikistan in 2007, in Kyrgyzstan, as well as in Afghanistan, doing similar projects and carrying out similar activities where we actually begin to set up and carry out geodetic measurements to fill in one of the biggest data gaps actually in Central Asia. So while we were doing field work, it became very clear to me that there was a missing link between the information that we were collecting in the field and the people who could potentially benefit from having access to that information. And these people that you see here at the bottom of this image, these are the very few survivors of a village that was almost entirely destroyed by the 2005 Kashmir earthquake. And they joined us in the field, and they were not only curious about the work that we were doing, they had a ton of questions for us. They were super curious, but often their questions were very important, such as, why do earthquakes happen? Or even, did we do something wrong that we had to be punished like this? So you can clearly see that there is a misconnect between the science that we do here, known as geodesy, and the people who can actually benefit from that science. So what do we do about that? I want to just connect these two dots for you. How can we go from geodetic data to people and to helping people prepare for earthquakes? So in this flow chart that you can see here, on the very top left corner, we're going to start there. So we start with GPS data collected in the field. Then we bring the GPS data into a program and we process the data. After the data is processed, we actually get a position for the point that we were measuring on the surface of the Earth and the position of that point through time. So the graph that you see here in the middle, these blue lines, this is basically a position of a point tracked over time. And the slope of that line is basically the velocity, how fast and in what direction that point is moving. And from that information, we can produce a map. That's the map that you see in the upper right corner. And this is a velocity map. And every red arrow there shows a position and the velocity of a point on the surface of the Earth as measured by GPS geodesy. Now, you may say, well, why is that important? What can we do with that information? The good news is, if we know the structural geology of this region, so for instance, if we know where the active faults are, and we can design our GPS network in a way that can allow us to understand the slip rate for these faults, so how fast these faults are moving. So if you look at the lower right corner of this flow chart, The black line represents an active fault that can trigger a devastating earthquake. And we have 2 GPS points, one below it, one above it. And if we know the velocity of these 2 GPS points and we subtract and take the difference, that difference basically tells us how much of that motion, that tectonic motion, is being taken up by the fault. So basically, how much of that motion is accommodated by that fault. And that's a really important information. And basically, the slip rate or this information is one of the most critical parameters that we use in order to produce fault hazard maps. Once we have a hazard map, we then need to know where the community is. So we basically map the exposure of the community. This is the locations of buildings and infrastructure. And we assess how vulnerable then the community is to the hazard. So as you can see, we can go from pure raw GPS data to potentially a hazard map that, if it's used in combination with other things, such as the exposure of the community, it can actually be a very useful tool for people to use. So here I'm going to focus on 2 sets of tools that we have developed over the last few years to basically bridge this information gap between scientists and at-risk people, specifically in Central Asia. And I'm going to focus on these 2 tools. So first, I'm going to look at the left side here, the educational materials that we have been developing since 2008. And these educational materials are developed for use in schools in Central Asia, and they are designed in a way that they not only communicate science-based information about earthquakes and why earthquakes happen and why Central Asia is prone to earthquakes, but also what kind of hazards are associated with earthquakes and what can communities do to prepare for those hazards. And what we discovered here is that communities that have a good understanding of the science of the earthquakes, they have a tendency to prepare better for earthquakes. So this was a very important link that we were able to make. I was also part of a group of scientists who put together a database of active faults in Central Asia. So that's what you see on the right side. So all those red lines are active faults. And you see also some blue and some orange circles. Those are the locations of earthquakes. And this fault database basically brings all the information that has been published so far by scientists into an online platform that is accessible by everyone. And all the data can be downloaded and used, for instance, by development agencies, by policymakers, or by just a member of public who is curious and interested about the locations of active faults. So what do we do with these materials? We test them in schools. We test them with people to make sure that they are actually effective in communicating information. So what you see here on the left side is one of our very simple models of a fault system that we tested with school children in Tajikistan. It's built out of very simple materials that can be obtained anywhere in the world. So we have a sandpaper, a rubber band, and a couple of wooden blocks. And just with a simple model, we are able to show in a very hands-on, interactive way the elements of an earthquake, the anatomy of an earthquake, all the things that need to happen in order for us to feel an earthquake on the surface of the earth. And then we also use that information combined with other materials to train teachers and even teacher trainers so that we can multiply the effect. And this way, we can basically use those teacher trainers to train other teachers in schools, in neighboring areas, to basically disseminate the earthquake information more effectively. So what you're looking at in the middle picture here are teachers who are exploring a very simple model of a landslide, trying to figure out how landslides occur, but also how earthquake can trigger landslides. And finally, we use these materials to train local scientists and members of communities in Central Asia who are in charge of hazard assessments. So for instance, this was a workshop that we did recently in Afghanistan to train the local scientists there and hence help to build the capacity of the locals as well. And finally, this is a brand new project that myself and my colleagues have been doing since 2017, 2018. And we are basically focusing on a very specific method called paired teaching. And this method allows for a scientist from anywhere in the world who would like to work with a teacher to bring his or her science into a school anywhere in the world, as long as obviously we can understand the language. And for some of these videos that we produce, we are also dubbing them into different languages. We're providing closed captions so that they can be accessible to more people. So the way it works is that you have a video teacher, and as you can see in the background here on the screen, who is going to demonstrate some topics, maybe pose some interesting questions. And the teacher in the class has the opportunity to basically pause the video in very systematic way in places that the teacher is actually supposed to pause the video, and basically take the teaching torch from the video teacher and engage students in his or her classroom in scientific discussions or hands-on activities. So by doing this, we again trying to bridge the gap between scientists and school communities, especially in parts of the world like Central Asia, where not a lot of international scientists can travel to, or even if they can travel to conduct science, they hardly get a chance to actually come to a school and share their science with a school teacher. So this is a really great opportunity for scientists, for instance, outside of Central Asia to get involved, but it's also very beneficial to teachers who are interested in bringing science into their classrooms. And a lot of times teachers feel a lot more comfortable when they co-teach a lesson with a scientist as opposed to being left alone. So we got to test these, some of these videos in Tajikistan in 2018 and 2019. And I should also say that we tested some of these videos in the UK in a school in London. And we got really interesting results that I would be more than happy to talk to you later. And finally, I want to emphasize that we do all sorts of interesting earthquake science. As you can see here, we do geodesy, we get involved in paleoseismicity, in seismology, we use historical earthquake data sets and combine that with the statistics so that we can actually feed the information in form of seismic hazards to at-risk people and those who may be able to minimize that risk. So these are earthquake engineers, maybe policymakers, people that work for the government, non-governmental institutions, and of course the general public. Now, I want to emphasize 2 points here. Now, we put a huge effort into seismology, geodesy, all these fantastic disciplines to produce these seismic maps that can improve our knowledge of earthquakes. But some of the most at-risk population still continue to live in very weak dwellings. So these are buildings that have been constructed very poorly and will most likely, these buildings collapse in a future earthquake. So I have been emphasizing a lot on education and awareness and bridging the gap between scientists and school communities and teachers. But please keep in mind that education and awareness alone cannot really save those buildings from collapsing during an earthquake. And as scientists, we need to really move beyond just doing science and working on the communication, but also thinking about some of the factors that are kind of not under our radar at the moment, things such as corruption, ignorance, lack of money, poverty, that really feed into increasing damage associated with earthquakes. Now, you may think that this is a one-way street, that we go from science to people, but actually people, communities have a big role to play in informing the science that we do. And indigenous knowledge, for instance, is one example of that. Local knowledge is very important and contribute a lot in preparation for earthquakes. And activities, for instance, such as citizen science can help scientists to collect data more effectively. Now, I'd be happy to discuss any of these items in more detail with you today or at a later point. So feel free to drop me a message later if you want to get in touch. Thank you.
Thanks, Solmaz. That's great, really resonant. And I know some of those points are particularly about how we engage with communities and also who are the key influencers, levers in the system about affecting change. I think we'll definitely come back to both of those. But anyway, let's crack on to Bruce Malamud, who's going to be from King's College. King's, sorry. I forgot where you were from there, Bruce. Who's going to be talking about multi-hazards and bringing, you're already hearing about the complexity of even just volcanoes and earthquakes, but actually Bruce is going to take it to another dimension. Bruce, you're muted.
And I muted on purpose so that people wouldn't hear me. Okay, so thank you very much, Ian. So I just wanted to start with a brief background of myself, which is I actually have a physics first degree from the US. And then I spent 2 years as a high school teacher in Niger in West Africa. And this really changed how I thought about the world because I saw these dramatic events occurring. I was in the Sahel and there were many windstorms and dust storms. And when the rain came, which was maybe 2 times a year, there was a huge amount of rain, and then the rest of the time it was dry. And so I moved over to the physical sciences, and I did a degree in the earth sciences for my PhD. And then 20 years ago, I started in a geography department here in London, where now I'm a professor of natural and environmental hazards. And so this period in Africa had a dramatic effect on me because I saw the world around me and the extremes that can occur. And so right now, after 20 years, my single hazard research focuses on landslides, wildfires, floods, earthquakes, and tornadoes. And my single hazard research, it looks at time series and mathematical models and spatial models. But more and more over the past 5 or 6 years, I've been working with social scientists and I've been working in the global south. And so this is an example from Nairobi that I took not that long before the lockdown in March in 2020. We were in Nairobi, and there we're working with a team of people to construct a history of what has been the flooding in Nairobi in the past. And we're using what are called blended sources of evidence. And so these range from Twitter to YouTube to instrumental records, etc. Now, a second major part of my research is on multi-hazard interactions. And so these are with natural hazards and anthropogenic processes. So what is a multi-hazard? There's many definitions for multi-hazards, but it's basically looking at all of the different single hazards that might occur in a given region. And so if I go back 2 slides here, here are some of the hazards that you'll hear about today. And what we've done is we've divided these, all the different natural hazards that we can think of, ranging from the geophysical, so we've already heard about earthquakes, we've heard about volcanic eruptions, to the hydrological floods and droughts, the shallow earth processes, the atmospheric, the storms and tornadoes and hailstorms, the biophysical, the wildfires, and finally, from impact events and geomagnetic storms. And so what we're interested in is looking at not single hazards alone, but thinking about what are the interrelationships between one hazard and another. And so this is an example from 1792 from Mount Unzon in Japan. And this is where a volcano erupted. This triggered a landslide, which then triggered a tsunami. And you can think of many different types of hazard cascades that might occur. And so in the lower right here, we see an earthquake can trigger a landslide, which can block a river, which can cause a flood. And so my research is looking at these hazard interrelationships, and I'll talk a little bit in the next slide about where I'm doing this research. And then also, what are the anthropogenic processes that might influence the natural hazards? And so these might be humans doing devegetation, burning things. It might be houses, and there's all sorts of anthropogenic processes that can come in. So my last slide here is where I'm currently doing research. So I've talked about Nairobi. I'm also doing work in Istanbul and Quito and Kathmandu. And this is a large project. It's a 20 million pound project called Tomorrow's Cities, Urban Risk in Transition. And what this project is, it's led by Edinburgh and King's College London, John McCloskey at Edinburgh and Mark Pelling at King's College London. And the aim of this project is to think about a step change for how we view hazards and risk in tomorrow's cities. What can we do? What can we change? And a lot of that work I'm doing right now is both single hazard focused, but more on the multi-hazard interrelationships. I'm also working in the Philippines on multi-hazard interrelationships. This is a photo I took, and no, the rainbow is real. It did occur. I didn't Photoshop that in when I took this picture. This is of Tal volcano. I'm doing work in UK and France. And then I have a large project which I'm co-leading with the British Geological Survey on landslides and the early warning of landslides. So I have various other research interests, but those are the main things, just as a brief introduction to myself.
Brilliant. Thanks, Bruce. So what you've really heard there from Bruce is that merging, that blending of all these, the different natural aspects of the hazard system, but then crossing over and having these interconnections with the human world. And I think this notion of risk contagion and systemic risk, of the interconnectedness of risk, is something that's really becoming increasingly evident in our hyper-connected world. So we now have in a situation like in 2011 Tohoku earthquake, where we have a large earthquake which triggers a tsunami, which is itself lethal. The earthquake really isn't in the same direct way. But then, of course, that tsunami knocks out a nuclear power station. That nuclear power station shuts down all the nuclear power plants in Japan, and actually encourages other countries like Germany to stop nuclear power. But back in Japan, actually increases the demand for fossil fuels, which actually starts to put fossil fuels back into more oil and gas burning in Japan because they've not got nuclear. And we bring in the effect of increased and enhanced climate change. So this is a complicated set of interactions, really, and that's what makes it so fascinating. And really, the last of the introductions is going to bring that to the fore, really, which is from Peter Stott, who's going to be introducing climate change more directly, but this complexity about how much of it's to do with humans and how much is it to do with the natural cycle. So Peter, please take it away.
Hello, and I'll also try and share a few slides as well. So just give me a second and bear with me while I do that, because so hopefully you can see those that first slide now. If I just go to right, here we go. So so we're looking at weather. Of course, I work at the Met Office, so we have a very long history of seeking to improve our weather forecasting and our forecast of weather. But I've been working actually in the part of the Met Office, the Hadley Centre, which is looking at how our climate is changing. And in order to illustrate the sort of work that we've been doing and I've been working on, I've got a couple of illustrations for you, because what we've been seeking to do is to really try to understand how our weather is changing with climate. And I chose this illustration partly because Verkhoyansk in Siberia has the most extraordinary climate naturally. The weather in the winter can get as cold as minus 67.8 degrees Celsius, was recorded way back in 1892. But in the June of 2020, temperatures reached 38 degrees Celsius, which is the warmest ever temperature that's ever been recorded north of the Arctic Circle. And when we have extremes like this, and there's a map there showing over a very large region of northern Eurasia in the winter and indeed spring of last year, temperatures remained extraordinarily high, about 5 degrees Celsius warmer over the whole 6-month period than the average. Then understanding enough people are asking the question, is our weather actually changing? Is it right anymore to look back at old weather records and think of those as a good record of what might happen in the future? And in many ways it isn't, because climate is changing. The greenhouse gases that we're emitting into the atmosphere is warming the planet, warming the atmosphere and the oceans. We're now over 1 degree Celsius warmer than we were in pre-industrial times, and the Arctic is warming up about double of that rate because of the effects of snow and ice melting, and the reflectivity of the Earth is changing. So we did a very rapid analysis. I say we, the Met Office led this analysis, and we worked with a number of institutes across Europe actually to look at this, and we figured out that these temperatures, particularly the really warm temperatures that we saw from January all the way through to June in Siberia, had been made 600 times more likely due to climate change. It was the most extraordinary result we'd ever had in this sort of analysis. And we did this basically by looking at climate models and by working out what the climate we would have had we not put greenhouse gases into the atmosphere, what the chances of having these extreme temperatures were. And actually it turned out that I think we worked out it would be about a once in a 80,000 year event without climate change that we would see 38 degrees C above the Arctic Circle. So this sort of science is now pretty robust and pretty, you know, we can do this on a pretty regular basis, and actually we can do this sort of analysis pretty quickly, because that's when the sort of timescales people want to know what is happening and what it means to them. But there are quite a few challenges that remain to us in this science, and to illustrate the challenges, I'm going to take you to South Yorkshire in the autumn of 2019, and the map on the left is showing the rainfall amounts that fell. Hopefully you can recognize the geography there. You can see where I'm from actually, which is Southport, which is just north of Liverpool. You can see on the left of the region there, but over to the east you can see the region of South Yorkshire, and those black areas, those very dark areas, are where rainfall was greater than 50 millimeters, and that led to widespread flooding. It led to 1,200 properties being evacuated, 120 million pounds of insurance losses during that flooding. And what we've been trying to do is try to figure out, has climate change had an effect on the risk of this sort of extreme and hazardous weather? And we've done some research at the Met Office, and we've got a paper currently under review looking at this. And we think that it has, and these sort of graphics illustrate that. We think that the frequency of having more than 50 millimeters in a day in the UK has increased by about 60% since 1900. And if we keep emitting greenhouse gases into the atmosphere, potentially, and that's a big if, of course, we may come back to that later in the discussion, but if we keep emitting greenhouse gases into the atmosphere, then by 2070, then there could be another 85% increase in the frequency. Now, bearing in mind that we all know that weather is very variable all throughout the world, and of course we also know it's very variable in the UK, but there are quite a lot of challenges here. And to do this sort of analysis, we need to use the types of model actually we use for weather forecasting. We need to have very high resolution of our models, for one thing. And then the other aspect that's very challenging and cutting edge of research is to try to figure out what this means for people. So this is both in terms of the flooding, so how does the water move across the land? So that's more in the geophysical system. But then we get onto the human systems, and it chimes in with some of the other discussion we're having, of course, tonight. Then we need to understand how people are affected and how people behave. So increasingly in our work, we're looking across the geophysical systems, and we're also thinking about how people take this information and how they can use it. So I'll stop there, and then we can move on to the general discussion.
Thanks for that, Peter. That's been really, really useful, and we'll definitely come back to some of those issues. That stuff in Siberia is just bonkers, I have to say. I've never seen that temperature difference is extraordinary. So I think what we'll do, maybe if we could have everyone up really, and I think we'll just one of the things I'd like to start with Becky on this, and then get other people's thoughts. But we have talked about, and I think it's appeared several times now, but just how many different approaches we have to bring together to look at these problems. They're so, these phenomena. Even if you just took volcanoes, that even within a simple volcanic system so complicated. So this idea about the disciplines we have to bring together. Now, one of the reasons I was keen to start with you on this, Becky, because it seems to me that volcanology in particular seems to have really embraced a hugely wide set of different kind of skill sets and disciplines to do that. Could you talk a little bit about that?
Yeah, sure. So there are a number of ways to study volcanoes, as I mentioned. But I think traditionally, if we go back, say, 20 years ago, that was your speciality. So you would do the geochemistry of volcanic rocks, or you would be a field geologist like myself, and you'd go out and study the deposits. And actually, we were very siloed in our disciplines, and there wasn't very much talking with each other. And I think that, and even the field volcanologists, so I tend to study pyroclastic density currents, and there would be another group of people who would study the ashfall and the eruption columns. So even with what looks like to be a small discipline, you'd have these tiny subset of experts. And I think what has changed over the last 20 to 30 years is the physical sciences becoming much more interdisciplinary. So we can only really understand a volcanic system, we can only understand a volcano if we use all these different approaches together. But I think what's been really revolutionary in volcanology in the last 5, maybe 10 years at the most, is looking beyond the physical sciences, looking at different approaches. So using historical data to understand volcanoes, using indigenous knowledge, oral traditions, looking at historical records and archives, and using all those different approaches to really tackle a problem. Trying to understand the impact of a community through art or creative writing. And this is where it's really exciting at the moment in our field, is now we're starting to work with a whole variety of people, from sociologists to artists to historians, to really try and tackle this volcanic system from a variety of angles.
And just before I just go on, I was going to go into Solmaz there, but one of the things that strikes me that is particular about volcanoes is you can see it. If you're living it, you've got this sometimes triangular shaped hill right behind you. So you have a relationship. Your communities will have a relationship to the volcano. That seems to be really important.
Volcanoes have appeared in human art since the beginning. Since humans have created art, they have drawn volcanoes. And that itself, I think, is fascinating. It's such an evocative part of people's lives. If you're living within the shadow of a volcano, a culture develops around that. And some of my work has been around co-volcanic societies. So how societies through time have learned to live with and evolve and actually embrace the volcano, either through religious culture or through other kind of means. And I think that's one of the things about volcanoes is their presence can weigh heavy on a society, but it also brings great benefits. So that they're not always a kind of like the volcan god type approach.
So I wanted to move to Solmaz because people don't have the same emotional attachment to a subsurface geological seismic fault line. However, your work has really picked up on this anthropological, almost ethnographic side of the relationship between people and their oral and cultural history associated with earthquakes. So, and that you fed a little bit of that. But again, talk about this interdisciplinary work. I mean, you a great example of trying to do that. How important is it?
Very important. And I just want to touch upon the fact that you mentioned people don't maybe have this intimate connection with what's underneath their feet. But they do have, actually. If you even when you talk to the Central Asian community, they may not have the same understanding as we have about what lies underneath our feet, but they do relate to earthquakes, to movements of objects, animals, that comes from legends and myths, and they connect that movement to what we feel as earthquake on the surface. So they do have this connection, except that this connection is a little bit different. And one of the big challenges is how do we actually recognize that and not write it off immediately, because this would be probably the easiest thing to do for anyone who is not familiar with that way of thinking, and quite honestly is really mean and is very ineffective. So they do have this connection. So recognizing that is very important, but at the same time, sharing the information that we have collected as scientists, what we know as evidence, in small dosages and in the most culturally appropriate way with local communities. Not necessarily telling them that this is the truth and you need to forget about everything else, but basically laying everything on the table for them and let them see it and pick what makes sense to them. And this approach, even though it's not very, some people might say it's not very direct, it's not very aggressive, I find this approach to work a lot better with Central Asian communities that often they have their own way of thinking about, how and why earthquakes happen. And as Bruce maybe could add to this later, sometimes even these legends and myths do have some connections with our scientific way of understanding how earthquakes happen.
Yeah, I mean, we'll go on to Bruce on that, but I think that geomythology is a really interesting area, because what are often these oral traditions talking about are really big events that have left an impact on the culture. And as scientists, the big events are sometimes the rarest and the hardest to get in our record. But Bruce, do you want to talk a little bit about that? Or about the importance, really, these different disciplinary?
Yeah. So just briefly, just to mention geomythology, I mean, there's many ways that we can find out what has happened in the past. And this is quite important because it gives us an idea of what's in the future. So what Solmaz is referring to is the idea of geomythology, or that legends, the Bible, Quran, that there are stories that might have as their basis actual events that have occurred. And so this is one of the more popular lectures that I give to my second year and third year undergraduates. Is we spend a couple hours on geomythology, and we talk about, what evidence is there for a flood having occurred thousands of years ago? Or what evidence is there for an earthquake or an asteroid impact? And often, like Ian is saying, either these are dramatic events which impact a large group of people, such as an earthquake or a volcanic eruption or an asteroid impact. And these can be passed down in oral history, which might be the stories that one group of people, Aboriginal people, might tell each other going down generations and generations. And so this allows us to have a picture into the past, sometimes as long as 4,000 or 5,000 years ago, which is quite amazing. I'll just stop there, Ian.
Well, I'm just going to pass on in terms of to Peter. I think one of the, in terms of the climate change bit, I think one of the problems is, there is that dimension, but often it's the difference between weather and climate. That event, particular events which have happened before and maybe even have been more violent in the past and more intense in the past, but the versus the longer trends, it's much harder to do. So is there any, looking at different disciplinary approaches to that, or is it, is it all going to be hard, straight physics and computer modeling?
Oh, well, there's quite a lot of computer modeling involved, but there is crucially, with all of that stuff, there's a lot of checking goes against the observational record, and actually we spend probably more time on that aspect than anything else. So the running of the models doesn't take very long, but the checking of those models, and as you say, the challenge comes for rare occurrences, very extreme weather. And one of the things that's bedeviled hurricane research, for example, in terms of climate change, is these issues about the observational record. But this is some of the approaches that we already touched on actually are coming in more and more in this field as well. So, for example, we're realizing that there's all sorts of evidence, documentary evidence, for example, from and there's a project called Old Weather, which if people are interested and they haven't heard about it, you can have a look at that. Which is a citizen science project where people are digitizing old ship's logs and so on. And that is helping us hugely, because what we can do if we have weather observations from ships that have been sailing across the oceans a couple of 150 years ago, whatever, we can then use those models, those weather forecasting models, to create the weather, but now informed not by informed by what actually was written down in the logs and so on, and people may have made their observations, and we can start to reconstruct what the likely hurricane record was, for example, in the Atlantic. And this is really important. So we do need these long records. We do need to use statistical methods as well to extrapolate the data we've got. But I think we can now start to get some pretty reliable estimates, especially when we look globally at how, for example, tropical storms are changing. And I think when we look at that data, it's pretty clear that the risk of the category 5 type of hurricane, for example, the most extreme category of these tropical storms, is clearly increasing. You see it in the data. You see the fact that we're seeing more and more of these. So there is a lot to do with these rare events, for sure. And this is where some of the uncertainty lies. But I think more and more it's becoming clearer about the signal of climate change on these types of situations.
And I'm thinking also, in terms of, say, the story in the Southwest USA with the mega droughts that happened, in 1,000 years ago, 800, between 800 and 1,000 AD and things like that. So we know in those places you can cripple very complex societies, and as a result of climate change. And I guess that's some of that in terms of the really big impacts actually quite important.
Yes, I mean that illustrates as you say, the vulnerability, and just a point there to make, I think, is that one of the important aspects of looking at extreme weather under climate change is that the vulnerabilities and the impacts are playing out in front of our eyes. And it's complicated to. It's not impossible, but it's complicated to model that in a computer simulation. But we have all of these examples happening, and so. But just to note, however, that the drought, in terms of weather categories, if you like, I think drought is the one where there's the most uncertainty, actually, because there's a whole lot of processes need to happen with a drought. In terms of the land surface needs to respond to the meteorology and so on. And things like mega droughts is a very good example of where, I think it's still at the cutting edge of really understanding what our exposure to mega drought is, actually.
Great. I'm always going to go on to talk a lot about communication, but you know what? The chat has been lighting up around issues to do with kind of social inequity and development. And I think that might be a more interesting place to go because we've variously touched on it. So I guess it's worthwhile going round again. Becky, you answered the question earlier on, but it's probably worthwhile picking up this idea about where volcanoes are and the relationship of studying them, saying a kind of wealthy, affluent, sort of developed nation versus developing nations, and it's in terms of the capacity to study these things, it's completely different capacity to study it. So can you say something about that those human inequities around the hazard world in terms of volcanoes, particularly, by all means, go broader.
Yeah, for sure. In terms of volcano science, I think there's a huge inequity, and I think that is something that we are really starting to grapple with. Volcanology has been a colonial activity. Much of the funding lies in Western countries, Western universities, and there's been historically a problem with parachute science. So volcanologists will go to an exotic location, they will study a volcano, they'll collect lots of data, often using local resources and local data collection. And then we come back to the UK or back to our Western countries, and then we work on that data and we publish it. And the application of that results and that research is disconnected to what the local communities really need. On the flip side, you've got volcano observatories in many countries that have a huge number of volcanoes. They're understaffed, they're under-resourced, there's not the funding for them, and they don't have this capacity to do research. So there's a bit of a disconnect between some of the research that's going on, and I think I hold my hand up to say that that's partly, I'm part of that problem, and it's something that I grapple with. So I'm trying to understand the very detailed processes of pyroclastic density currents, and I say that it's ultimately the aim is to reduce that hazard. But there's that, do we really need to understand those detailed kind of nuances or the crude tools are what's needed by the volcano observatories, given their resources and their funding? Do we need more and more elaborate computer models, or do we actually need better ways of education, communication, pouring that funding resources into the volcano monitoring in the local communities? And I think that's something that we are really starting to get anxious about and try to understand our role in as volcanologists. And
it's probably worthwhile just reminding people, if they need reminding, about the Sendai framework. And the Sendai framework came in for disaster risk reduction, came in 2015, and really promoted a very different approach to disaster risk reduction, which focused on being much more people-centered, much more inclusive, working with those communities that were ultimately at risk of these disasters and all the rest of it. And so I think that's, and I was thinking about that business of community engagement. There are lots of different ways of actually involving communities. And Solmaz, I mean, you already demonstrated some of this. So can you say a little bit more about? And it came up in the chat. Really, I saw a question about how do you engage people in these processes? I mean, how do you go about it? Oh, you've given us some indications, but tell us more.
Yeah, I mean, at the very most basic level is that we as scientists, when we show up somewhere in the world, let's say Central Asia, we are not just only scientists, but we also have this chance to really communicate what we know with people. So I can give you an example of, just a case that when we were in the field and setting up a GPS station, and there are, of course, a number of people watching from far, and a typical response could be that, okay, they're just watching, or even worse, saying something like, gosh, when we leave this equipment here and come back, nothing of it is going to be left here because those people are going to come and take it away. But there is also another approach, and I'm really happy that I tried to do that when I was with my colleagues in the field. I said, well, look, if we have this concern that maybe this equipment is going to get damaged, let's invite them, let's talk to them. They're obviously curious, they're watching us. So, but in order to do that, first of all, you need to be able to talk to them. So you need to know the local language. So if you're a scientist and you're by yourself there and you can't connect with the people, this is a big issue. So that's why we should always, and for many other reasons, work in partnerships with local scientists and basically not only learn from them, but also teach them what we know. And so in this case, we invited the people, they came, they had lots of questions. They didn't know what a GPS station was. They were thinking that we were burying some precious item under the ground, and we resolved that very quickly. And not only that, these people from the village became the guardian of this unit that was set there for many years. So they were charged by the task to take care of it and make sure that it is actually, continuously measuring information and sending the information. So we shouldn't shy away from interacting with people, and we have to do the opposite, basically. We know that they're curious, and just draw them in, speak with them, talk to them, learn about their concerns, and how we can actually help to build a more effective scientific program that not just only focuses on the science, but also brings benefit to the communities we do science at.
That's interesting. And the question just popped in the chat before I go to Bruce, which says, and anyone can answer this one, do you think there's a way that hazards may bring opportunities for development? I mean, in my head, obviously volcanoes bring in huge geotourism, and that kind of it, and certainly eruptions. Many volcanologists, I say, have flooded to the volcano to watch it. We're all watching Etna at the moment and various others in Indonesia. But what do you think? Do you think it could be beneficial to have a hazard on your doorstep? Anyone can jump in here. Silence.
Well, I don't think an active fault is quite interesting to look at. Maybe for me, yes, but I don't think people will fly to come and see an active fault that looks very inactive.
But there is a thing. I mean, I know this is where the question's leading, but there is a kind of disaster tourism, though, isn't there? I mean, they are fascinating, and I think I pulled my hand out. I think we're in some ways the worst culprits. We are fascinated, and there was there is an awful tendency. One of the things I often say is that volcanologists in particular often go there to see the volcano erupt, and so that hence is there's more volcanologists killed by a volcano prediction they've made than seismologists killed by an earthquake prediction, because earthquake predictions are terrible. But there is a fascination about going to these places and seeing it, and it is kind of difficult. But Bruce, I wanted to this idea of you mentioned the global south, you mentioned social inequities, and you've obviously been in those places. It's probably worthwhile maybe setting the scene, because the Tomorrow Cities project is an interesting one, because it is trying to address. I mean, the mission is to reduce the disaster risk for tomorrow's poor, but it's part of a bigger push, I'd say, certainly within UK science, about trying to address these social development issues. Can you say more on that?
Yeah, I can. And just before we do, I just wanted to mention briefly on the opportunities that both disasters bring and that hazards bring. And it is very clear that although disasters can damage the economic and other aspects of the trajectory of whole countries for many years to come, they can also provide opportunities. And that has been shown over and over again, that after disasters, there's been redevelopment, and that a whole area has been reinvigorated. This is not to minimize the effect of disasters, but there is very strongly, and this has been shown in many places, not just disaster tourism, but actually long-term benefits that have come from disasters. Now, in answer to your question, there is a strong move now for the research funding environment to ensure that research is not just scientists going out and doing their physical science or their social science research. And so an example is Tomorrow Cities, which you've just mentioned, where part of this £20 million, before it was even awarded, we worked with people in each of these cities. We got the people that were involved that would be working with the policy, with the government. And so we worked on, from the beginning, what we call of co-design and co-producing the products. So one of the comments in the chat is there's a gulf between the scientists and the government, and therefore that is what often contributes to disasters. And I think a lot of times now in research grants, and I know for myself, I will not get involved with money coming from the UK government unless I am thinking about the legacy aspects of how is this going to make a difference, and how will the science that I'm working on as a physical scientist actually be brought into the planning. So one aspect is, are you co-designing the research, or is the UK coming in with their scientists and saying, this is how you should do your research, here's a fancy model, and now we are going to leave, and good luck with the model? Or are we making sure that we're co-designing tools and methodologies that can be used by the Global South after the research grants are done? So that's one aspect. The second aspect is that Tomorrow Cities is not trying to change the current cities, the landscape of hazards, but rather really trying to focus on what is going to be a change for tomorrow's cities. And so it particularly involved a lot of planners in our thinking. And so we're thinking about, well, what are your plans for Nairobi, for Istanbul, for Kathmandu, for Quito, for 10 years from now, for 20 years ago? And can we be doing things that are affecting how you might plan for the future in terms of hazard, exposure, vulnerability, and ultimately risk?
Thanks for that. In terms of moving on to, I'm getting a little bit of feedback there. Peter's one, I was interested in, climate change is an interesting example, because the biggest impacts are already being seen largely in those distant margins, those communities, South Pacific Islands or Inuit communities, etc., and things like that. So it's already picking up on social inequities, but and I guess it's a big push around adaptation because of that. Can you say more about, I know that's not necessarily what your work is directly on, but certainly at the Met Office has got a lot of interest in that type of work as well.
Yes, and like Becca was saying in her context, I mean, we're acutely aware that a lot of this research has happened in richer countries and developed countries. I'm part of a European project, for example, where there's a lot of European Met services who are very interested in this sort of work. But we have we've got more and more colleagues, scientific colleagues around the world who are interested in the type of work that we do, and are collaborating with us. So, for example, we have a project spinning up in Southern Africa. We've done quite a lot of work in parts of Asia, and we're also doing work in South America as well. So part of that is about the basic capacity building in the scientific arena, to build that knowledge and to collaborate together. So one of the fascinating aspects of my science for me is that there's common techniques and common understandings that we can share, but of course each individual region and locality has its own particular weather and its own particular way in which the weather then interacts with the land surface and then indeed the people who live there. So there's the local knowledge is of course essential, and so these partnerships that we're starting to develop now are really fascinating areas to work in, and we're just beginning to touch the surface of how we can then use that knowledge with local people. Because one of the things that Bruce said is something that's about rebuilding following weather disasters. We've worked with the Red Cross, Red Crescent, and one of the things that they really value with this type of work is that it provides a more informed context for that rebuilding, because there's a real moment of opportunity there to build back. But of course, to build back in the context not necessarily of the past weather statistics, but in the context of what those weather statistics will change in the future, i.e. in terms of climate change.
Thank you for that. And I just noticed there's a really good question that's come in, which is almost exactly on what I was going to throw in next, which is this, and some people have kind of just touched on it. We're doing all this clever science, all this very sophisticated science, and ever more with more and more techniques, etc. But one of the things that struck me, I guess, maybe 10, 15 years ago was the fact that, for example, in my area in earthquakes, people were dying with it was the same things that were killing people all the time. And it was things we'd known about for 100 years. And so to what extent do we need more science, or to what extent do we need better communication of what we already know in order to help the mitigation? I know, Becky, you've got some thoughts on that.
Yeah, I think the difficulty with volcanology in particular is that there are relatively rare events. And I think that whilst they are a dominance in the landscape, a volcano might never erupt for a community's lifetime. They have another pressing need of other hazards, pressures from other socio-economic circumstances, poverty perhaps. And so it's very difficult then for the communities and for government to necessarily direct the funding that is required into very detailed volcano monitoring, which is essentially what's needed. So then when a volcano does awaken and starts to look like it might erupt or start erupting, then there is a lack of that infrastructure around that volcano. But it's difficult to argue for that funding to go in that direction when that volcano might not erupt. And that's one of the difficulties, I think, around volcanology, is the uncertainty of these kind of things.
And I remember talking to a colleague who used to work in the Caribbean, and he was, he'd be pulled into the government, and he'd be wanting more money to be done on, monitoring volcanoes that he thought could erupt. And the governor would say, will it erupt this year? And he said, well, we don't know, not really, maybe not. Will it erupt next year? Will it erupt the year afterwards? And his point was, we know we're going to get a hurricane this year. We know we're going to get a hurricane within the next 3 years. Where do you want me to take my money kind of away from? And one very quick question before I go into so much. How much do you hate Yellowstone, Becky? Because this is one of these other ones which comes through, which people have in their bonnet, particularly dangerous volcanoes. Whereas I think for many of us, it's the everyday hazard of everyday volcano or earthquakes that's the problem, rather than I guess the equivalent for earthquake on this is a San Andreas or something like that. But how do you deal with that? Just before we go on to SOMAs, how do you deal with these fixations with the big ones?
That's on my bingo card of questions for these types of events. It's Yellowstone, and mega tsunamis is normally the other one. And I think that's part of the problem is these huge eruptions capture people's imagination, and they have these very large death tolls. And so there is a sense of urgency about trying to understand that, maybe predict that, and worry about it. But something that I learned actually relatively recently, and as a volcanologist, I'm a bit ashamed about this, but the most frequent cause of death in a volcanic eruption is ballistics. And that's a volcanic bomb. So that's a piece of tephra, anywhere from fist size up to car size, flying through the air. Doesn't actually kill in the large quantity, through time, huge quantities of people, but it will kill a few people every year or so, every couple of years. Places like White Islands that erupted, Mount Ontake, this is what was responsible for those deaths. And so I think it's very easy to get distracted by things like Yellowstone, and I think they are a distraction. And actually, we should be thinking about the much more common occurrences and the much more common and frequent hazards that the communities living near volcanoes are facing.
In some ways, I mean, I was kind of half joking about earthquakes, but I mean, what do you think? Is it new science we need, or is it old communication, or maybe it's new communication that we need?
I think we need all of that. Yeah. New science for sure. I mean, we are learning so much and so quickly. I mean, just taking the recent earthquake in Nepal, the Gorkha earthquake, was one of the largest earthquake that scientists for the very first time were able to actually really document well, because of all the seismometers, all the GPS stations that they have been able to set up there prior to this earthquake. So they really documented this event really well. And this is Nepal, and not everywhere is Nepal, right? If we go a little bit more west in Central Asia, the network of GPS stations and seismometers is quite sparse. So we do need to continue producing more data and also increasing the accuracy of the data that we are collecting. So there's absolutely no question about that. We also need to look more into the past and try to figure out, when these historical events happen. That's really like a biggest gap that we have in our understanding of how often some of these large earthquakes, especially, for instance, the earthquakes related to the Himalaya, occur. So not only look at the present time and into the future, but also go back and try to learn as much as we can about what has happened in terms of seismicity in the past. So science has to move forward. Communication has to also move forward along with science. We cannot separate these. And we have to figure out the most effective way of communicating with a very diverse groups of people in different parts of the world with very different concerns and questions and cultural background. So there's always going to be work to be done on these two fronts. But what is at the end of the day, in the context of earthquakes, is going to really make the difference, as I said, is the buildings people live in, because most of the injuries are actually related to buildings collapsing, or even the content of the buildings causing deaths or injuries to the people who are in the building during the shaking. And as long as we cannot fix that, it doesn't matter how much information, scientific information we have collected, how much effort we have put into developing great communication strategies. But at the end of the day, if a family is living in a building that's going to collapse, none of that is going to matter, and none of that is going to save their lives. So we have to pay particular attention to what the actual causes of deaths are and how we can basically address that missing link.
Just before I go on to Bruce with that, I mean, that's a really interesting point. And you touched on corruption earlier on, and we know that the levels of corruption correlates with the levels of fatality. It does, for example, in earthquakes, to that proxy of building collapse. But I guess the question is that something the hazard scientists should be dealing with? Because first, if you've come through a physics route, that seems really far away. Dealing with corruption, that's not my game. But do you think we should be starting to take all of that on board?
We need to be part of the team that's going to resolve this issue. We are not the answer. We are part of the solution. Yep. So the way I see it is that, no, it's not like you burden the scientists with all of these, important tasks, but we need to be in the communication with policymakers, with those who are doing development projects, whether it's governmental organizations or non-governmental organizations. And this is already happening in many parts of the world and also in Central Asia, that scientists play a more active role across sectors. And we should, as scientists, I think, make ourselves available to such activities and not shy away saying, oh, I'm just a scientist, this is not my problem. Yeah. This is a part of a bigger picture. Yeah.
Bruce, I suspect you've wrestled with the ethics of this as well, in terms of the role of the scientist who just does the science and then writes reports, stops, versus getting your hands dirty and maybe, hazards and disasters are political incidents, and in many respects, providing knowledge and information can actually be providing political information in certain places. So, how do you tackle that ethical minefield?
Well, there's various parts of the ethics, and they range from, are we getting our science to the correct place? And are we having, who is it we're getting them to, down to the community level, which is now what is starting to concern me a lot, which is if I do a better hazard map for a given region, have I just affected the livelihoods of people who are living there because their insurance premiums have changed? Or maybe it's an area without insurance premiums, but there's something else involved. One of the first projects that I did, which is now, I'm embarrassed to say, 18 years ago, was my first funding, was actually on heavy metal contamination. And I was looking at extreme heavy metal in Zambia. And I was shocked when I found out that by using a group of farmers to investigate the extent of the problem, which was actually quite bad, we had just affected their livelihood because people stopped buying from them. And so it was a real wake-up call. And I was like, oh my gosh, I didn't consider the ethics of this. And I was very upset. So the way I've been dealing with this is because I am a physical scientist. I am numerate. I work with physical models. I make sure that I am working with social scientists and I'm thinking through the ethics quite carefully. And so we think through who is going to be affected by what I am doing. The other thing is who do we need to contact to affect change? There are official government laws in many places, if we go in the global south, if we go in the UK, if we go in France, but then there are what Mark Palin calls shadow actors, people that you actually have to talk with to get the change affected. And so one of the first things I do now for grants, which I wouldn't have done 10 years ago, is we do what's called an institutional mapping. We map out what are the relationships of the different people, the different organizations, the different laws to affect change in the thing that you are trying to change. Now, often this is more difficult with very small amounts of money, which is one thing that I've seen now changing in the UK is the grant funding for natural hazards. They're larger and larger grants now, and they tend to be asking for large multidisciplinary teams to address that.
I'd like to move on really kind of the final kind of substantive bit. We'll do another quick round robin to Peter, because there's a lot of mention in the chat around climate change futures, etc. And one of the things that struck with two aspects, I guess, is that a climate warmer world is going to be a more hazardous world, that we're loading the dice in a whole bunch of ways, and you've talked about some of them. But the other thing is the drift towards the climate engineering. And as one of your colleagues one told me, we get to the stage with our detailed knowledge of the climate system that we could, for example, make rain fall in the Sahel, but it might increase hurricanes in Florida. And so it seems to me that you guys, the climate priests, are going to start in a very position where many of these ethical dilemmas will be dropping on your desk. I mean, you've obviously thought about it. What's your take?
Yeah, that's right. I think, and you're right to portray it as something that's coming towards us, if you like. Maybe we're, slightly behind the other guys on the panel here, but we're catching up fast, if you like. So there's the question of so-called geoengineering. That's right, and if we start modifying the weather, there's some pretty serious ethical issues out. But we're already facing the ethical issue around the work we're already doing. Because the question that we've been focused on really is, how is climate change, like you say, loading the dice? How is that changing the dice? But that's, of course, only one component of the issue. And, very much chiming in with discussion in other hazards, the way people are affected by these extreme weather events is as much about their exposure and vulnerability as it is to the hazard. And so, there are questions around there's the whole what's so-called loss and damage agenda around the negotiations around climate change, which are very loaded with ethical questions. And one of the issues there, one of the many issues there, is that if we are blaming, so to speak, it on climate change, what I mean there is the impacts on people on climate change. That may well not be the whole story, and it may allow other actors to escape their culpability in not helping people become more resilient to the weather. So it is this whole ethical dimension is something that we are now indeed grappling with, and seeking to like Bruce was saying, collaborate with colleagues who have more experience of some of these issues.
So we're just in the last couple of minutes, so I thought maybe just to wrap up, maybe go around the panel and think about what is the key thing or things that, from your personal perspective and over the next few years, you think is really important to deal with in the context of the hazard setting. So Becky, you're coming back off of maternity leave, so you've probably got lots of things on your head. But in terms of volcanoes, what are you looking forward to get your teeth stuck into?
I think there's a couple of kind of big challenges to volcanology. I think I've talked already about the challenge of taking the detailed physical science and turning that into applied science, working in partnership with the communities at risk.
Yeah.
I think there's the big question around uncertainty with volcanology. So a volcano can erupt in a multitude of different ways. It may or may not erupt. You can have long, protracted volcanic crises, which looks like it's going to erupt, and that never happens. Mm-hmm. And so you have a difficulty with maintaining relationships with community, with governments, with policy, maintaining an awareness and trying to communicate that uncertainty around that without then losing the being accused of crying wolf. And I think that's something that is going to be a real difficulty as our tools become more sophisticated and we feel like we are getting better at maybe forecasting, to on the flip side to acknowledging that great uncertainty we have around these events. Great,
thanks. Solmaz, how about for you?
I think for me, building the capacity of local communities to carry out earthquake-related research is really important in Central Asia. I've been involved in earthquake research for the last 15 years and with various institutions from United States, and from across Europe. But I really think now, especially, is the moment for Central Asian countries to really lead earthquake research in partnership and collaborations with international scientists. And so one of my goals at the University of Central Asia at the moment is to basically set up a geophysics lab where local scientists can receive training, and we can also apply for equipment so that the local scientists have their own equipment of measuring and also have the training to process, analyze data, and publish, get the data out. As opposed to have it being the other way around. And so that the local scientists can, walk together along with international and visiting scientists. And I think this is really important.
Fantastic. Very quickly, Bruce.
Yeah, very quickly, I'd say one of the great challenges is making sure that we genuinely are bringing up a generation of educated physical and social scientists in the context of natural hazards for the global south, which is something I think is fundamentally missing right now, and it's just not there.
I agree completely with that. Last one to you, Pisa. What are you going to be working on?
Okay, so it's got a couple of things to mention then. So first of all, to understand, and this is related to how we're going to adapt to climate change, understand much better about droughts, hurricanes, tornadoes, and the impacts of those in terms of agriculture, in terms of health, in terms of flooding and so on. And I think we're making great strides in that. And the final point, I think, is that it feels to me like, and many climate scientists feel this, we feel on the cusp of a much more hopeful future around climate change in terms of reducing our emissions. And I think one of the things I really hope that I can do in my career, hopefully, is to actually notice that in the geophysics, to actually notice that we've changed the trajectory from the ones that I've been talking about for the last 25 years of my career of increasing temperatures and so on, to the temperatures starting to change in a positive way so that we minimize the impact of these hazards.
Here, fully endorse that. Listen, thank you, everyone. Thank you for taking us through. I've actually found it, normally these things are kind of full of doom and gloom and, death and destruction, but this has really been uplifting and it's been fantastic. So thank you, Becky, Solmaz, Bruce, Peter, and thank you everyone out there for sticking with us. And that was our Hazardous Earth. Thank you.